All right, lads and ladies, welcome back to MAC 1105 College Algebra on the 11th of January. I know it might seem strange to see me wearing a mask, even though I'm at home. My son is sick, and so my mother, his grandmother, is here to kind of help us take care of him and also maintain schoolwork, all of that stuff. It looks like I may have contracted COVID, so in order to minimize the probability of giving that to her while she's here, I am masking. So I know it's a little strange, but that's what we're doing, right? Just pretend like we're out there in the real world. This is how things have been for the last couple of years anyway. You may have noticed, you may have noticed that I posted a link in Canvas to a Discord server. I will show you these really quickly. Here it is. I think this is yours. This is a nice place for you guys to chat, talk about homework problems. If you're struggling with something, you're having a hard time with a problem, go ahead and post it up here, right? Tell people what you've tried, take a picture of your work or a screenshot of the problem, see what other folks say. You can get really good feedback from your peers this way. The link to join the Discord server is here in Canvas. Just go to the announcements. Same place that you came to find the link to get here for our meeting. Go to this announcement, click this link. The invite links for Discord only last for like a week, maybe 2 weeks, I forget. So I advise getting in there and joining soon before that link expires. I will try to replace it as it expires, but generally I'll be a few days behind knowing it expired. I won't know it expired until someone told me because I don't pay that much attention to it. But yeah, that's all. I recommend you guys go ahead and join that Discord server, talk with your classmates, kind of treat it like how you would have a conversation in the hallway. If something's bugging you, you want to complain about my handwriting, or you want to talk about a problem from any of the homework sets or anything like that, feel free to do that here. Yeah, that's that. The other thing, of course, your very first homework set did come due today. Let me take a quick peek here. Just to remind you, in my open math here, your first homework set and the tutorials were all due today. So if you didn't get time to get those done, just follow the procedure we discussed on the first day. Let me know you need more time on the assignment, and I'll go ahead and try to open it up for you. The big ones, of course, were homework 1 and quiz 1. Those are the guys that we really want to make sure you get done, because those are the things you need to have internalized at this point in order to be with me as we move on to the next bit of material. Okay, that's the stuff that we wanted to talk about at the start. Let me get the document camera up and we can get rolling on the new stuff. Today, we're going to talk a little bit more about domains. We're going to talk about graphs of functions, and if there's time, we're going to get into the material on linear functions. So some of this we've kind of brushed up against already, but we're going to treat it a little more formally. This, of course, is MAC1105. The section number is 015, which means this is college algebra. And the date today is the 11th of January, 2022. As I said a second ago, today, we're going to be talking about the homework 2 stuff, and the bulk of that is graphs of functions. And we're going to be talking about domain, range. We're going to be talking about increasing and decreasing functions, or intervals of increase and decrease. We're going to be talking about mins and maxes. And then we may also talk a little bit about linear functions. I think we'll probably get to some of this, which is homework 3 stuff. Where we'll talk about, the definition, forms of a linear function, definition, and recognizing a function as linear. We'll talk about slopes and rates of change. And forms. I'll say forms of a linear expression. These are the things I expect to get through today regarding linear functions. We may also talk about horizontal and vertical lines and parallel and perpendicular lines if there's time. And then on Thursday, we're going to talk a little bit more about other homework 3 stuff, namely this thing called linear regression, which is going to involve a meaningful amount of calculator work. So I just want to remind everybody that you do need to have a calculator, something like this, right? This is the TI-84. You can use the 83 if you want also. This is an 84 plus. Just a quick reminder that the 89 and the TI Inspire, the fancier ones, are not allowed. When we use calculator stuff, rather than asking you to somehow try and decipher what's on my calculator on the document camera there, I am going to use this emulator. It takes a little while to boot up. There it goes. I wanted to give you guys a heads up because I know, oh shit, come on. Please work. I want to give you a heads up that there is a calculator workshop at the Learning Commons. So this is something that you'll almost certainly want. If it comes here to events, there's one on test anxiety. This is very good. A number of my students have really enjoyed this. Study smarter, not harder, some study techniques, right? Take a look at the workshops that are offered by the Learning Commons. There should be, oh, I don't see it. There should be a calculator workshop in here somewhere. Let's see, here's 1033 calculator videos. That couldn't hurt. Graphing calculator help, yeah. So take a look at these down here also. I'm going to post this link in the chat. And I'll post it in the Discord also. So take a look at those. I think they will be helpful to you. The 1033 calculator videos, these are also going to be good, right? These are also using the 83 or 84, I think. And it'll help you get comfortable with the graphing calculator, which is, if I'm honest, a kind of complex piece of hardware. Here's the emulator. So when you see me use stuff here, it'll look like this. All right. So we talked last week about what functions are, the definition of a function, and how to recognize whether the thing you are looking at is or is not a function. Either thinking about it as a mapping diagram or a table. Remember, a function is a relation that sends every element of the domain to one and only one element of the range. In other words, every input goes to only one output. There's no input that gets sent to 2 different outputs. Such objects have graphs. So the graph of a function, this is the set of all ordered pairs in the XY plane of the form something, comma, f of that same thing. So this is your input or x value, right? It's an element of the domain. And this is your output or y value. And it's the output associated with this particular input. So if I do a quick sketch here of just a kind of random looking function, this up a little bit for you. Okay, so some things you're going to see when you look at graphs. Usually you'll see y equals f of x written somewhere on the page. And you'll see the horizontal axis labeled as x. I've labeled just a few points here. You see this ordered pair whose x value is 1 and whose y value is 1 is on the graph. Right, this is the point 1, 1 on the graph. And we could say that since 1, 1 is on the graph, f of 1 is equal to 1. Right, so the x value here is 1 and the y value here is 1. This is the ordered pair 1, 1. This is your input and this is your output. And remember that this output is always f of this input. The next ordered pair that I've labeled explicitly here is 3, 2, right? You've got 3, 2, so the x value there is 3, the y value there is 2. We always put the x value in the first coordinate, the y value in the second coordinate. And we could similarly say, since 3, 2 is on the graph, f of 3 is equal to what? Yeah, very good. Chidi got it in the chat there. F of 3 must be 2. Right, so this is, let me annotate here. This y value is f of that x value. This y value is f of that x value. Then I have one here that's kind of generic, right? The x value here is a, but I haven't labeled the y value here. So can anybody tell me, in as much detail as we can, what is the y value at this ordered pair, this point on the graph whose x value is a? Remember, you can hold down the space bar to talk and just shout out, or you can type in the chat. Looking for the y value of this ordered pair. And I'm not looking for a number. We could call it b if we wanted, but trying to sort of follow this logic, right? Yeah, Lexi got it. I apologize for the very open-ended question. So the thing I'm trying to drive home here is that the y coordinate is always f of the x coordinate. So this 2 is f of 3. That's kind of what we're talking about down here. So if all I know is that this is a, right, the x value here is a, and I'm on the graph, then the y value, whatever that is, must be f of a. This might seem like one of those duh things from all those questions you answered back in middle school and high school, but believe it or not, I have a lot of questions on my calculus exams where students, if only they could remember that the y value at any point on the graph is f of the x value, they would be fine. So this sort of trivial observation, believe it or not, is going to be very, very helpful for thinking about graphs of functions, not just in this class, but in more sophisticated classes as well. Okay, so the graph of a function, you just take your xy plane and plot all of the points that are of the form some number in the domain, comma, f of that number. And that will give you a curve or a straight line, or a smattering of dots. It'll give you some points in the plane. And for most functions, that will be some sort of curve. Every x value coming from a point on the graph is an element of the domain. And every y value from a point on the graph is an element of the range. So you can look at the shape of the graph and where it is placed in the XY plane and come up with your domain and range. Usually we report these as intervals. So the way I usually tell students how to do this, I call it the smooshing game. So we're going to talk here about finding domain and range. And we're going to do it from the graph. We call this the smooshing game. Which has another name. If you want to be formal about it, it's called projection. Not in the sense that psychologists use the word, like you're projecting your problems onto somebody else, but mathematicians use the word projection to describe what happens when you kind of imagine shining a light on a geometric object and seeing where the shadow is cast. So let me just give you a quick, simple example here. Let's say this is the graph of my function. Y equals f of x. So this is the graph of the function f. And I want to find its domain and range. What I mean by the smooshing game is that you can take the graph, which is all the ordered pairs here, all the points here. There's infinitely many of them. I want to be clear about that, right? These points are infinitely small. And so in order to get a connected line segment like this, you need infinitely many points. So there's no way I can list all the numbers in the domain or list all the numbers in the range. We're going to have to describe these as intervals. If I imagine taking this graph and I have the hydraulic press channel guy here. He takes this graph and puts it on the hydraulic press and he goes and smashes it down onto the x-axis. That will tell us the domain. All right, so again, imagine I've got a big heavy thing up here and I'm just going to go until the thing splats on the x-axis. What gets hit? Well, what I see is that this point would get smooshed down to here. A point in here would get smooshed down to here. A point here would get smooshed down to here. A point here would get smooshed down to here. A point just to the left of this guy would get smooshed just to the left of 4. So if I want to, I can highlight down here everything that gets hit when I press or project that graph down onto the x-axis. The other way to think about this is if you have a very bright light source up here that shines straight down, where is the shadow, right? The highlighter would be the shadow from a very, very bright light source shining down from above, hence the term projection. The only thing we want to be a little bit careful about, you'll notice I've kind of filled in the circle on this end and I've left the circle on this end open, right? So this point projects down or gets smooshed down onto the x value 1. All of these points project down onto all of these x values. this point, if it were filled in, would project down onto the x value 4. But this point is open. And perhaps you remember from previous algebra classes what that notation means. That means that there is not a point on the graph here, right? There is no point on the graph here at 4, 1/2. This being open means that the line segment continues and gets as close as you want to that point, but does not actually hit that point. So if I wanted to include some delimiters here, that's the name for brackets and parentheses, I would put a bracket on the 1 because the 1 does get hit, and I would put an open parentheses on the 4 because the 4 does not get hit. So smooshing the graph onto the x-axis gives us that highlight interval there along the x-axis, and that interval is the domain. So the domain here is 1 with a bracket up to 4 with a parentheses. All right, this is how we find the domain from the graph. You smash the graph onto the x-axis and then see what interval on that x-axis gets hit. The range is the same thing, you just do it onto the y-axis. Smooshing the graph onto the y-axis tells us the range, right? So remember, all of the x values on this graph are elements of the domain. So when I project onto the x-axis, that tells me the domain as a set. It tells me what all of those x values are as an interval, and that's the interval 1 to 4. All of the y values are the outputs. So if I want to know what is the set of all outputs, aka what is the range, I want to just find I want to describe the set of all the y values here. And to do that, we smoosh the graph onto the y-axis. So now my hydraulic press is coming in from this way, and it's going to go, and it's going to smash the whole graph onto the y-axis. I see right away that this point would get smooshed onto the number 3. A point right here would get smooshed onto whatever this y value is here. A point in here would get smooshed over here to whatever this y value is, all the way until you get down here. And then the open circle here would get smooshed onto the y value 1/2. And remember, the open circle means that there's not actually a point there. So the 3 gets hit. Purple. The 3 gets hit. The 1/2 does not get hit. And everything in between gets hit. So this is your domain, and this is your range. So then in interval notation, what is this range?
Would it be 3? Oh, they said.
Yeah, very good. A few people have it in chat there, and I suspect Lexus was about to say it out loud. We remember when you're writing an interval notation, you always put the smaller number on the left, so it would be the interval from 1/2 up to 3. Since the 3 does get hit, this point actually smacks the 3. And since the 1/2 does not get hit, this open circle smacks the 1/2. We would use a parentheses on the 1/2 and a closed bracket on the 3. All right, so that's how you find the domain and range. These can be a little bit more complicated. This is just sort of a toy example. So I'm going to do one more example, and then we can move on to the next little bit here. One of the families of functions we're going to talk about a lot this semester are quadratics. So let's take a look at one of those. Let's find the domain and range of the function graphed below. We haven't talked about how to graph these sort of functions yet, so I won't ask you to come up with the graph on your own. Let's imagine we have something looking about like this. Okay, the shape is called a parabola. Functions that have graphs that look like this are called quadratic functions, and we will study them in detail a little later in the semester. But for now, I'm just going to call this f of x. And we'll worry about those graphing details a little later. Remember that these arrows mean that the graph continues going like that forever, following the pattern it appears to follow. So like you see this branch here going down and to the left, this arrow means it's going to keep going down and keep going to the left forever and ever on end. Same thing here. This guy going down and to the right means it's going to keep going down and to the right forever and ever on end. Okay, I think this time it's easier to start with the range. So let's do the range first. And then we'll do the domain. So if I take my hydraulic press and I apply it to the graph of this function, and here it is smushing, 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 smushing the whole thing into this, into the y-axis. This point right here will get smushed over to the 3. And all of this portion of the graph and all of this portion of the graph will get smooshed onto the y-axis. So the 3 does get hit, gets hit by that vertex point. Remember that point up there is called the vertex. When I smush that vertex over onto the y-axis, it hits this y value 3. And then all the other pieces of this graph hit all the things beneath that. So 3 gets hit. Everything from 0 up to 3 or 3 down to 0 gets hit. Everything down below gets hit too, right? This arrow continues going down forever. So there is a part of the graph that's down here that would get smushed onto whatever part of the y-axis is down here. So this business continues down like that forever. So can anybody tell me what my range is? Can anybody tell me at least one of the endpoints of my range?
Is it 3 negative infinity?
Very good. Those are both of the endpoints. How would I write that in interval notation? Everything from negative infinity up to and including 3.
The negative infinity first.
Very good. Negative infinity is definitely smaller than 3. So I would say here that my range is negative infinity to 3. Remember, the smaller thing always comes first. All right, bracket or parentheses on the 3?
Bracket on the 3.
Definitely a bracket on the 3, right? The 3 does get hit by a point on that graph. All right, slightly silly question. Bracket or parentheses on the negative infinity?
Bracket.
So it's
Parentheses.
I say slightly silly because it really is. Infinity is technically not a number, right? We cannot arrive at infinity. So I can't say that there's a part of the graph that actually hits negative infinity. It's just sort of a notation to describe this graph going down forever and ever. So it will always put a parentheses on the infinity symbol. Infinity symbol, by the way, has a name, in case you want to impress your friends. Add it over here as a note. It's called a lemniscate. Oh, some fluff on my pen. And if you take Calc 2 with me, We will talk about lemniscates in general when we talk about parametric curves. Okay, so the range, we smush this whole graph all over here onto the y-axis. We see that the 3 gets hit, and then everything beneath the 3 gets hit, which means my range is -infinity up to and including 3, which is parentheses, -infinity, comma, 3 bracket. Bracket means included, parentheses means not included, and we always use parentheses on the infinity symbol. I'll add a separate note here. Okay. Now let's do the domain. So first, let's talk about smooshing down from above, because we haven't had to look at something like this. If I smoosh like this onto the x-axis, this vertex will come down here to smoosh onto. Any part of the graph here will come down and smoosh in here. So smooshing down from above, we get just this. Is that the whole domain here? Is there a part of the graph that has not yet been smooshed to the x-axis?
I think there's more to it.
Yeah, Samantha's correct. There is more to it, right? I've only smooshed kind of the dome, right? I've only smooshed this part. But remember, these keep going forever and ever, right? This graph really continues out like this. And this guy really continues out like this. So stuff outside of this interval also gets hit. You have to imagine smooshing up from the bottom as well. So it's really more like this portion of the graph that extends over here going to the right and down forever. If I smoosh it up onto the x-axis, we'll hit everything over here. And similarly, the part that goes down and to the left over here forever really does go to the left forever, and he will hit everything over here. So if you zoom out enough, what you'll see is that every part of the x-axis gets something smooshed onto it eventually. So what does that say about my domain? Yeah, we've got it in the chat there. The domain is going to be -infinity to +infinity. Excuse me. Okay, so domains and ranges from the graph, it's not too bad. You have to imagine just projecting or smooshing the graph onto the x-axis to get the domain and onto the y-axis to get the range. Sometimes one is easier than the other. Take your time, think about it. If you've come up with an answer and you're not 100% sure it's correct, ask yourself, is there any part of the graph that hasn't been smooshed yet? Right, like we did when we found everything from here to here, coming from the upper part of the graph, but missing everything outside. We said, okay, well, this part of the graph down here hadn't been smooshed anywhere yet. He needed to get smooshed up. And same is true for this part of the graph. He needed to get smooshed up. And if you're ever stuck on this, remember the actual definition is the set of all x values. So if this graph is allowed to continue this way forever and ever, and this way forever and ever, there is a point somewhere on this graph with x value -10. It's just way the fuck down here. There is a point on this graph somewhere with x value +100. It's just way down there. We're looking for the set of all x values for the domain, the set of all y values for the range. Working with graphs is good, but it's not the only way to find these things. So if you want to specifically find the domain, sometimes it can be easier to find the domain from an algebraic expression than from the graph, especially if you don't have the graph. Finding ranges from the algebra expression can be a little trickier. We will talk a tiny bit about that later in the term. But before I wander away from finding domains and ranges, I want to talk a little bit about how to find those things, specifically the domain algebraically. There's some rules I'm going to give you now that we will lean on, we'll rely on for the rest of the term, and I will expand on a little bit as we move further through. So So we talk about finding domains algebraically. And this one's fun because there's some language choices here that I think are memorable and silly enough to stick in our heads. I like to talk about what are called domain red flags. Right, so ladies, you ever go on a date with a guy and he talks endlessly about how much he hates his ex or how much he hates his mom? Fucking red flag, right? That's some shit you need to pay attention to. All right, functions have personalities. They have red flags also. So here they are. The red flags you need to watch out for when you meet a function. Does it have any variables downstairs in a fraction? Right? Are there any fractions in this representation of the function? If so, look at the denominator. Are there any variables showing up anywhere in that denominator? If there are, you need to make sure that the bottom is not 0. Right? Any values of those variables that would make the bottom 0 need to be kicked out of the domain. The other one I'm going to share with you right now is variables under an even root. Right? Like under a radical, square root, fourth root, sixth root, and so on. Here, you need to make sure that the inside is greater than or equal to 0, right? We cannot divide by 0. That's the first rule. And we cannot take the square root of a negative number. That's the second rule. So for example, if I have something like f of x equals the square root of x plus 1 divided by, let's do x minus 2 times x minus 5. This is a function. We won't play with functions like this until much later in the course. It's fairly complicated, but I just want to illustrate these red flags. I see both of these red flags. All right, here's a fraction, and there are some variable quantities downstairs in that fraction. This is the first red flag. Also, there's an even root here, right? This is a square root, and there are some variables inside of it, namely this x. So I have the first red flag. I do have some variables downstairs. So I need to make sure that that bottom is not equal to 0. How do I do that? Well, let's set the bottom equal to 0 and find out what gets kicked out. So let's solve x minus 2 times x minus 5 is equal to 0. There's something you may recall from 1033 or high school algebra classes called the zero factor property or zero product rule. If you have two things multiplying, like we do here, x minus 2 is being multiplied by x minus 5 equaling 0, the only way that can happen is if one of them is 0, right? How can you multiply two numbers and get 0? It's only possible if one of those numbers is 0. If neither of those numbers are 0, like 5 times 7, you're never going to get 0. But if one of those numbers is 0, like 7 times 0, then you will get 0. So this means that either x minus 2 is equal to 0 or x minus 5 is equal to 0. Adding 2 to both sides here, we get x equals 2. Adding 5 to both sides here, we get x equals 5. So if x is equal to 2, then this expression, which is the denominator, will be equal to 0. And I need the bottom, the denominator, to not be equal to 0. So from these, we learn that x cannot be equal to 2, and x cannot be equal to 5 in our function, because these make the bottom equal 0. And that's no bueno. The other red flag we have here is variables inside a square root. And we need to make sure that the inside is greater than or equal to 0. The square root of 0, by the way, is fine. The square root of 0 is 0, but the square root of negative anything is a problem. So here, if I set the inside is just x plus 1, right? That is the inside of my square root here. I just set that greater than or equal to 0. And solving this inequality is not hard. You can just subtract 1 from both sides, and you get x is greater than or equal to -1. So we have the following requirements for our domain. We know that x is not allowed to be equal to 2. X is not allowed to be equal to 5. And x must be greater than or equal to -1. So let's sketch this on a number line. I'll put -1 here. I'll put 2 here, and I'll put 5 here. My first requirement is that x is greater than or equal to -1. That means x is coming from the interval bracket -1 to infinity. But as I march up, I get to 2 here. I know that x is not allowed to be equal to 2. So I need to chop the 2 out. And then I keep going to the right until I get to 5. And I say, oh shit, x is not allowed to be equal to 5 either. So I chop the 5 out. Here's your domain. So these are all the numbers that are bigger than or equal to -1 and not -2, not 2 and not 5. All right, in other words, everything from -1 up to and not including 2 is good. Everything between 2 and 5 is good, and everything bigger than 5 is good. 2 and 5 themselves need to be eliminated, and everything to the left of -1 needs to be eliminated. So the domain here we can practice writing our interval notation. That's -1 up to 2, parentheses on the 2, bracket on the -1, union with 2 to 5, parentheses on both sides, because we do not want to include 2, and we also do not want to include 5. And then we union that with 5 to infinity. Right, any questions on this? So the question there was, how do I know to use a union? Well, I want to talk about these things, and these things all thrown together into one basket. And the union is the set operator, which does that. So what I'm trying to do is just describe the set that I've sketched here kind of as a single set. And I know that I'm allowed to have the stuff from this interval, the stuff from this interval, and the stuff from this interval, but nothing else. So I just write down those intervals with unions between them. Cool, cool. All right. Let's talk about increasing and decreasing. That's enough on finding domains. Finding ranges algebraically, by the way, is much harder. If I wanted to look at this function and figure out its range without graphing it, that's quite tricky. I will show you some things that work for certain functions later in the semester, but for now, ranges we always get from the graph. So remember, the definition of a function, every input goes to one and only one output. One of the reasons that definition is so useful, right? One of the reasons we kind of restrict our attention to study relations that satisfy that rule is because you can tell me where you are on the graph just by telling me the x value. If you tell me the x value, the input, there's only going to be one output associated with that x value because of the definition of a function. What that means is above or below each x value, there's only going to be one point on the graph. So if you want to locate a position on the graph of a function, it is sufficient to just tell me the x value you're talking about. And I will know which y value you're talking about by looking at the graph, because there can only be one of them. When we say a function is increasing, what we mean is that as the input gets bigger, the output gets bigger. And when we say a function is decreasing, what we mean is that as the input gets bigger, the output gets smaller. So I have here the graph of a function. Remember, the inputs, the x values, get bigger as we go to the right. Yeah, like maybe here's 1, here's 2, here's 3, here's 4, here's 5. The x's are getting bigger as we go to the right. And the y's get bigger as you go up, right? Like maybe here's 0, here's 1, here's 2, here's 3, here's 4, and 5. They're going up to get bigger here, and they're going to the right to get bigger here. So when we say a function is increasing, this means the outputs get bigger as the inputs get bigger. And we say a function is decreasing that means that the outputs get smaller as the inputs get bigger. The kind of analogy that's useful here, just think about time, right? Like if I want to track my bank account's balance over time, if my money is going up as time goes up, then I would say that my balance is increasing, right? If my money is going down as time goes up, I would say my balance is decreasing. More generally, you can replace time by any input, right? The x values here don't have to be time. They could be lots of things. But if as the x values get bigger, the y values get smaller, that means we're decreasing. And if as the x values get bigger, the y values get bigger, that means we're increasing. Same sort of idea. Geometrically, since going to the right means getting bigger for the inputs and going up means getting bigger for the outputs, you can think of this like a little dude walking along the graph. This dude always walks left to right. That's his shtick. All he can do, right? He's like Zoolander. He can't turn right, whatever, can't turn left, I forget. This dude can only walk to the right. If he's going downhill, then the function is decreasing there. And if he's going uphill, the function is increasing there, right? Since he's always going to the right, the x's are always getting bigger. So we're just asking, are his y's getting smaller, i.e. is he going downhill, or are his y's outputs getting bigger, i.e. going uphill? So just think of a little dude walking along the graph, going from left to right. If he's going downhill, the function is decreasing there. If he's going uphill, the function is increasing there. So walking left to right. Downhill means decreasing. And uphill means increasing. I remember what I said a second ago when we first switched over to talking about intervals of increase and decrease. If you want to tell me where you are on the graph, like suppose you want to tell me you're at this point on the graph, or this point on the graph, or this point on the graph. If you tell me the y value, I might not know which point you're talking about, right? This particular y value here, there's 1, 2, 3 points on the graph, at least. But if you tell me the x value, there is and can only be 1 point on the graph that has that x value, because the definition of a function is every x goes to only one y. The reason that's important here I'm going to put this in here as a note or a warning. We always, have I said always enough? We always report increasing and decreasing as open intervals of x values. And it's that last part that people mess up. Never tell me you're increasing at a certain y value. There could be 5 different points on the graph that have that y value, and maybe you're increasing at one of them, maybe you're decreasing at one of them. Don't tell me you're increasing from this point to that point. Also kind of nonsensical. I don't know which direction you're talking about going. Just give me the interval of x values, right? Now, there's a reason why we always use open intervals. I'll talk about that in just a second. But it is the case that we always use open intervals of x values, not y values. Telling me the y value does not uniquely determine a point on the graph. Telling me the x value does uniquely determine the point on the graph. I'll say one more time. When you're telling me where a function is increasing, tell me the x values. When you're telling me where a function is decreasing, tell me the x values. Right? I hate taking off points for this on the test because I know everybody can point to the part of the graph that is increasing and decreasing, but the notation matters. How you tell me matters. All right, so for this graph, for the function graphed above, we are increasing where? What open interval of x values has this guy walking uphill?
Is it a number or just a?
It's A to B.
Yeah, A to B, right? From right here to right here. It's exactly this part of the graph where he's going uphill. So this would be the open interval A to B. And when I write an open interval, I like to say the interval, because this is the same notation as an ordered pair, right? It's possible to confuse yourself and talk about intervals and ordered pairs in the same notation and get a little bit crossed up. So yeah, this interval right here, we are increasing here. Now I'm going to ask you in a minute, are we increasing at A? And am I increasing at B? And I want that to boil in the back of your brain for a second while we figure out the interval on which we are decreasing. Remember, the arrows mean continues like this in that direction forever and ever, continues like this in that direction forever and ever. I think we would all agree that this portion of the graph is decreasing. Right? So assuming that this graph goes on and on and on forever, going to the left and up, what interval of x values is associated with this far left portion of the graph? Yeah, Haley got it in the chat there, from -infinity up to A. And always open intervals, always. Does everybody see that? The x values, the interval of x values associated with this part of the graph is everything to the left of A. So from -infinity up to A. Similarly, over here, if I want to talk about where we're decreasing, that's everywhere to the right of B. What is that in interval notation? I'm going to put a union symbol here. What is the second interval on which this function is decreasing? Yeah, very good, from B to infinity. If I'm being especially picky, I would say it should be a lowercase b, but I know what you mean here. Beautiful. All right, these problems can get more complicated. Before we dive into the slightly more complicated examples we're going to look at, what's going on at A and at B? So here we're decreasing. And over here, we are also decreasing. All right. So right here at A, my little guy is coming down, coming down, coming down, coming down, and then he turns around and starts going up, going up, going up, going up. Would it be fair to say we are decreasing at A? Am I going downhill right at that point?
It might be.
It's an interesting question. So I've got one person in chat saying no. We've got one maybe. I would say that right at that moment, I'm doing neither. Right? I'm very briefly, the word would be instantaneously, in transition from going downhill to going uphill. So when I take a step forward from here, that step forward is going to be a step up. And when I arrive here, the step that lets me sit on A, that was a step down. So the step in was a step down, and the step out is a step up. So right there at that moment, I'm doing neither. I'm neither decreasing nor increasing. I'm not going downhill. I'm not going uphill. The same thing is true here at the top of this little hill here. The step onto this point would be a step up. The step away from this point would be a step down. You've experienced this in your car, right? When you drive over a hill at speed in your car, as you're going up the hill, you're kind of pressed down into your seat. And as you're coming over the hill, you're very briefly weightless, right? You get that like feeling in your stomach as you ride over a hill, that kind of like roller coaster feeling. That weightlessness is you instantaneously transitioning from going uphill to downhill. So right here at this point, you're not going uphill or downhill. if you think of it in terms of physics, your velocity vector would be horizontal here. You're pointing straight ahead. You're not pointing up, you're not pointing down. Just to the left of this, you're pointing up. Just to the right of this, you're pointing down. But right there at that moment, you're looking straight ahead. And the same thing is true here, right? Just to the left of this, you're looking down. Just to the right of this, you're looking up. But right there at that point, you're looking straight ahead. So at these transition points, sometimes called turning points, right? Turning points where the graph turns, you're neither increasing nor decreasing. And that's really the big reason we use open intervals. I don't want to include A in the interval of increase because I don't want to say I'm going uphill here. I'm not. I'm looking straight ahead. I'm not going uphill. I'm not going downhill. Same thing. I don't want to include B in either of these. If I included it in the increasing, I'd be saying I'm looking uphill at this moment. And I'm not. I'm looking straight ahead. If I included it with a bracket here, I'd be saying I'm looking downhill at that moment. And I'm not. I'm looking straight ahead. That's why we always use open intervals, right? At those endpoints where we transition from one to the other, we're not doing either of those things. There's a more subtle reason behind this. And that is that, how do I say this nicely? In terms of rates of change, we can talk about, and we will talk more about rates of change very soon. We can talk about the rate of change over an interval, right? Did you increase over that interval or decrease over that interval? What is the slope like from those one point to the next point? But talking about the slope instantaneously at that moment is quite challenging. It requires some calculus. So to answer the question, am I increasing at a point, right, rather than over an interval, requires calculus. And it turns out that the calculus required there leads to an inequality, and the solutions to those particular inequalities are always open intervals. All right, so this is the definition of increasing, decreasing. Quick note, it is also possible for a function to be neither increasing nor decreasing on an interval. So maybe just another quick example. Okay, here's the graph of a function. We could talk about its domain and its range, and we can talk about where it's increasing and decreasing. The real reason I wanted to introduce this particular function here is because there is a certain interval on which this function is neither increasing nor decreasing. So let's begin by finding the intervals of increase and decrease. So the function f graphed below where am I increasing?
At 2 to 4.
Very good, right? My little dude walking along this graph, I'll draw him over here. He takes a little tumble and eats some shit, but then he gets up and keeps walking here. And then at some point, he's going to arrive over here. He's like, you guys, I know this is going to age me. You guys ever heard of the game Lemmings? Right. Nope, never mind. This guy's like a lemming from the game Lemmings. Same people who made Grand Theft Auto way back in the day made a game called Lemmings. Check it out if you want a good retro game. Anyway, my little dude, he's going to start over here. He's going to walk, walk, walk. He's going to fall down here. He's going to walk, walk, walk. He's going to come over here. At this point, he's going uphill, right, through this segment of the graph. And like I was that Samantha said that that's from 2 to 4, and that's correct. What sort of delimiters should I use? The endpoints 2 to 4.
It should be open, right?
Yeah, very good. Open, so parentheses, not brackets. And it might be nice to say the interval. So you don't confuse it with the point 2, 4, which is not on this graph. Okay. Where am I decreasing? Where's my dude going downhill?
-3 to -1.
Yeah, very, very good, right? This portion of the graph, which means we're talking about the x values from -3 to -1. Brackets or parentheses?
Brackets.
So this is good. I designed this particularly to be a little bit sneaky. You see the filled in holes there, right? And we want to say that that's a bracket thing, right? Filled in bracket. But remember, when we're talking about increasing or decreasing, we're always going to use open intervals. I cannot say for sure I'm decreasing at this point because this point is infinitely narrow and I don't know what's happening over here. In fact, there's nothing happening over here. So really the only place I can say for sure we're going downhill is strictly between these points. At those points themselves, something else could be happening. Like here, my dude is in the act of falling as he gets to this point. And over here, he didn't exist to the left of this. I can't say what that step was like for him because there was no step to take. So I can really only say that he's going downhill strictly between those points. So again, as counterintuitive as it may seem, always open intervals, and of course, always x values. So this would be the open interval from -3 to -1. And now there's a portion missing, right? There's a portion that I have not yet described. This piece. When my dude just walking along flat ground, he ain't going uphill, he ain't going downhill, so he's not decreasing, he's not increasing. We would say that the function is constant. Right? Constant function means the outputs don't change. As I walk from like 0 to 1 here, my inputs are getting bigger, but my outputs aren't going up and they aren't going down. So the function is always returning the number -1. The output is -1 everywhere through here. So we say that the function is constant on the interval from -1 to 2. And again, I would use open parens there. For example, at 2, am I increasing or am I constant? I step in here constant, I step out of here increasing, but right at that moment, what am I doing? Neither. So that's the openness of these things. It's a little bit wonky, but just remember when you're asked about increasing or decreasing, you're always going to give open intervals of x values. As long as you remember it like that, you never have to waste time on them. Right, any questions on increasing, decreasing constant functions? Okay, I have one more thing I'd like to talk to you about. Finding the domain and range here could be a cute example, but we only have a few minutes left, so I want to talk about average rates of change really quickly. I need to give you the definition. I'd like to talk more. We'll talk more on Thursday, but at the very least, I need to define for you this concept called average rate of change. So he said if your outputs go up as your inputs go up, that means you're increasing. If your outputs go down as your inputs go up, that means you're decreasing. How quickly your outputs go up or how quickly your outputs go down is your rate of change. The definition average rate of change, by the way, I'm going to abbreviate as AROC because it just takes a while to write. The average rate of change for the function f on the interval, I'm going to use closed interval here. This can also be said as from x equals a to x equals b. Instead of on the interval a, b, you could say from x equals a to x equals b. It means the same thing. Is the following expression. F of b, the output at the right endpoint, minus f of a, the output at the left endpoint, divided by b minus a. Upstairs here, this is function notation. This is not multiplication, right? This is f of b, not f times b. You cannot cancel anything here. Don't try to cancel anything here. That's not how it works. Like you can't factor out the f and then cancel the b minus a's. That's not what this notation means. For those of you familiar with the concept, and I'm sure all of you are, this is actually a slope, right? This is the slope of something called the secant line. I have a function looking like this. A is over here. Maybe B is over here. This is the point A comma f of A. And this is the point B comma f of B. You're going to take the y value here minus the y value here and divide that by the x value here and minus the x value here. And I'm sure everybody knows, even though we haven't said it yet this semester, that that is a slope. It's the slope of this little dotted line I'm drawing in. That's called a secant line. Okay. I think there's one other thing that I wanted to define for you. So if you're asked to calculate the average rate of change for a function, you'll use this definition. And I'll make a little note here that we need to talk about this more tomorrow. Did I have this here? Maybe it's not. I thought. I want to take a look at your homework. There's something that I think is in your homework that we haven't talked about. So I'm going to pop that up really quick just to make sure I'm not forgetting something. Pretty sure they asked you a few questions about mins and maxes. Oh, maybe not. Maybe not. Maybe I'm forgetting. Well, it doesn't look like it. All right, then I think we did good here today. don't know why I thought I saw that. Oh, wait, here we go. Yeah, okay, there's this one question asking about mins and maxes. So I'm going to hold you for a few extra seconds here. This is the definition of average rate of change, and we will play more with this next time. The other thing we'll play more with next time mins and maxes. There are several flavors of these. I'm going to just define local min and local max for you here. And I'll use a similar looking graph. Let's toss maybe one more little whoop-de-doo on there. So remember, this point would be a comma f of a. This point would be b comma f of b. This point up here would be c comma f of c. And this point down here would be d comma f of d. All the concepts that we've talked about today kind of tie together, right? Average rate of change is connected with increasing and decreasing. Mins and maxes are connected with increasing and decreasing. And next time I'll try to show you some insight there, and also start talking about linear functions. So a min and a max. A max is a point on the graph that is taller than any of the points nearby. Specifically, we call these local mins and maxes. So a local max is a point on the graph which is taller than any point nearby. And when I say nearby, what I mean is that you can put a little window, right? Some window, however small, such that if you just look in that window, that's the tallest point. All right, if I were to zoom in and ignore everything else, this point right here is the tallest point. So if you can find some window that makes that point the tallest point in that window, then that point is a local max. And the same idea for a local min. If you can find some window that makes that point the smallest or lowest point in that window, that makes that point a local min. There are other kinds of mins and maxes called global or absolute maxes and global or absolute mins. Those you just remove the window, right? If it's the tallest point anywhere, then that is a global max. And if it's the lowest point anywhere on the graph, that is a global min. So local and global. Mins mean small point where the output is low. Max means tall point where the output is large. And then a local max is a max that is only a max if you look nearby. Maybe there's another point on the graph somewhere that is taller, right? Like this arrow continues up over here. So there's a point on the graph somewhere over here that's definitely taller than this. But if I pay attention just to what's going on nearby, this is the tallest point in that window. So here we would say F has local mins at x equals b, and also x equals d. And remember, if you're wanting to report the location of a feature on the graph, you can just tell me the x value, right? Because of the definition of a function, there can only be one point at a given x value. So it suffices to just tell me that the min is at x equals b. If I ask you, where is the min? Tell me the x value. If I ask you, where is the max? Tell me the x value. And f has a local max, or has local maxes at x equals a and x equals c. So if I ask you where is the min or where is the max, I want the x value. If I ask you what is the min or what is the max, I want the y value. We'll talk more about the difference between local and global maxes next time. We'll also do some examples calculating average rates of change. I'll connect this to the study of linear functions. And we will go as far as studying something called regression, linear regression, next time on Thursday. Now, you now have everything you need to finish the second homework and second quiz. I strongly recommend you do that before Thursday, at least the homework, right? Get in there, do on that, work on that, because there's another homework set, homework 3, that I'm going to open up for you. You can work on it if you want, but it's going to be due next Tuesday. So before I let you go, let's take a quick peek back over at mom. Line up math, and make sure we understand when things are coming due. So homework 2, I have set to be due for you on the 13th, right? That is Thursday. Homework 3 and quiz 3, I'm going to move these to be due for you on next Tuesday. So on the 13th, homework 2 and quiz 2 will be due. That is at the start of our next class. Homework 3 and quiz 3 will be due next Tuesday at the start of class. That is going to be the 18th. That is 18th. Due on the 18th at 9:30 a.m. Let's save those changes. That's homework 3. Quiz 3, I'll do the same. So what is due for you at the start of class next time? Homework 2 and quiz 2. All right, you got to do those. And then homework 3 and quiz 3, those will be due next Tuesday. And this is how it's going to roll, right? Pretty much every day of class, you're going to have a homework and a quiz due. It will be the homework and quiz and material that we talked about the previous day. This way you stay on top of your shit. This is how you want to do it. All right. So work a little bit homework 2 today. Tomorrow, finish up homework 2, work a little bit on the quiz. Make sure you have both of those done before we meet on Thursday, the 13th. And then on Thursday, the 13th, we're going to talk about linear functions, a lot more about rates of change and linear regression. Those will then be due on the 18th, next Tuesday before class. That's it from me for today, guys. Everybody take care. If you want to talk to me, I have an office hour from 11 to 12. You can also Canvas message me or chat in the Discord. I'll be watching all those things. Otherwise, I'll see you on Thursday.